In Minecraft Java, we have 3 dimensions: overworld, nether, and the end. The end should be the one that surprised and astonished players most, where some of us had never seen the true structure of the end. Just as when people discovered the Earth is a ball, I found it extremely unbelievable when I heard that the blocks would disappear suddenly at some places and reappear again. It was still unreliable for me that until I double-checked the circumstances in my world. The next question is, why does this happen? I mean, which line of the code let everything occur? This video is made based on this thought, from the perspective of a freshman undergraduate who is not majoring in computer science and has never written Java code before. So to understand all of these easily for both you and me, let's begin with the basics of computers. Binaries, used commonly in every computer, can represent numbers and values by the on and off of anything. For example, lights, switches, etc., etc., etc. The tower of computer science is built up on this logic, and by logic gates, we can accomplish all kinds of manipulations on binaries, additions, subtractions, multiplications, and divisions. For additions, we can consider it as 2 binary numbers being added together, bit by bit, just like how we do it in decimal. Each bit can either be 0 or 1, and when we add them, we have the rules 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals 0 with a carry of 1 to the next bit. The result of the addition is a new binary number that can represent the sum of the 2 original numbers, which can use XOR gate to calculate the sum bit, and AND gate to calculate the carry bit. When it turns to subtraction, we can use the same logic as addition, but with a twist. Still, we can design gates to calculate the difference bit by bit, but we need to calculate the borrow bit as well. The rules for subtractions are 0 minus 0 equals 0, 1 minus 0 equals 1, 1 minus 1 equals 0, and 0 minus 1 equals 1 with a borrow of 1. However, this is not as straightforward as addition, because we need to consider the borrow bit and how it affects the next bit. In order to simplify the circuits, we can use a technique called complements. There are 2 types of complements: the ones complement and the twos complement. The ones complement is simply flipping all the bits of a binary number, while the twos complement is flipping all the bits and adding 1 to the result. By using NOT gate, we can flip all 0 into 1 and all 1 into 0, which is pretty easy. And as you can see, the twos complement is based on the ones complement, but with an additional step. Thus, it is also easy to implement. Then some smart babies would ask, why do we need complements? The answer is simple, because it makes subtraction easier. Instead of having to deal with the borrow bits and the complexity of subtraction, we can just add the twos complement of the number we want to subtract. This way, we can use the same addition circuits we have already designed, and it simplifies the design of computers. We can prove this by using an example of 5 minus 3. In binary, 5 is 101 and 3 is 011. The twos complement of 3 is flipping all the numbers 011 into 100. Then add 1 become 101, so we can add 5 and the twos complement of 3 to get a result. 101 plus 101 equals 1010. Reject the first carry, we got 010, which is 2 in decimal. The reason we reject it is that we are only interested in the last 3 bits, which represent the result of subtraction. This is how we use complements to simplify subtraction in computers. By only additions, we can achieve the same result as subtraction, and it makes the design of computers much simpler and more efficient. Thus, if we store the twos complement of a number in memory, we can easily perform subtraction by adding the twos complement of the number we want to subtract. But how does it work? If we list out all the numbers in binary, then we get a list of complements as follows. As you can see, decimal minus 15 equals 1's complement, and decimal minus 16 equals 2's complement. If we use 1's complement, we can represent both positive and negative numbers, but we have two representations for 0, which is not ideal. However, if we add 1 to the 1's complement, which has only one representation for 0. This is why we use 2's complement in computers, because it simplifies the representation of numbers and makes it easier to perform arithmetical operations. And to prove that it really works, let's imagine a clock with 12 hours. We can represent the time as a number from 1 to 12. From the form you can see the midpoint is 6 o'clock, and the number after 6 are negative numbers. Thus, we have clockwise to 3 to represent 3 o'clock later, and counterclockwise to 9 to represent 3 o'clock earlier. In this way, if I want to calculate what time is it 2 hours earlier than 5 o'clock, I can just take 10 for 2 hours earlier, and 5 for 5 hours later, then add them together, which is 15. But we only have 12 hours on the clock, so you would directly take the 3 o'clock, which is 15 minus 12 equals 3. This is how we can use complements to simplify subtraction in computers. By only additions, we can achieve the same result as subtraction, and it takes the design of computers much simpler and more efficient. For different number of bits, by using 2's complement, we can represent both positive and negative numbers. For 4-bit system, we can represent numbers from -8 to 7. So as to 8-bit system, from -128 to positive 127. 16-bit system, from -32768 to 32767, and so on. The range of numbers we can represent is 2 to the power of n, from -2 to the power of n-1 to 2 to the power of n-1 minus 1. Now, some smart babies would also ask, what if we add another 1 to the maximum value? This causes overflow error, which is the error occurred when the value exceeds the maximum value can be expressed by the number of bits. Let's see an example. For decimal number 2147483646. Here we have the first bit and the last bit as 0, and the other 30 bits are 1. If we add 1 to it, it will become O with another 31 ones. These two numbers share the first bit as 0, which means they are both positive numbers. However, if we add 1, it will become 1 with another 31 O's, which is a negative number, minus 2147483648. While in Minecraft Java editions, the integer numbers are represented by 32 bits, and it allows us to represent player positions, block size, and so on. However, if we try to represent a number that is larger than the extreme value, we will get an overflow error. This can cause unexpected behaviors in the game. This code is used to generate the height value of the n dimension, and it works well for most cases. This line of the code is used to ensure that the height value is within the range from -100 to 80. And the name error with none is only a temporary variable to hold the error value, although it really goes wrong sometimes. The two nested loops iterate over a range of values to calculate the island density. The math square root x times x plus z times z is used to calculate the distance from 0, 0, and the result is multiplied by 8 to get the final coordinate you see in Minecraft. This means that each chunk, which is 16 times 16 blocks in size, is conceptually divided into 4 parts, each 8 blocks times 8 blocks in size for generation purpose. So how does this strange phenomenon of blocks disappearing and reappearing actually happens in game? To understand this, we need to take a look at the line. For the max square root function, it calculates the square root of the sum of the squares of z and x. But in Java, since Mojang didn't project against overflow, when x times x plus z times z exceeds the maximum value, it wraps around to an active value due to integer overflow. This causes max square roots, x times x plus z times z, to return nan, not a number or an active value, which leads to blocks disappearing and reappearing unexpectedly. Let's take an example. Suppose we have x equals 46,340 and z equals 0. Then x times x plus z times z will be 2,147,395,600. At this point, since this number is smaller than 2,147,483,647, it will not overflow yet. Please remember that x here is not the coordinate you see in Minecraft, but only the number of half chunk index. Thus, we can still see blocks at the point scaled by 8, 370,720, y value 0. But if we increase x to 46341, then x times x plus z times z will be 2,147,488,281, which exceeds the maximum value. This causes an overflow and the result wraps around to an active value. And we take the square root of this negative value using max square root, it returns not a number. Thus, after scale by 8 at point 370728y0, there are no blocks generated. However, things do not end here. When we still increase x and z to larger values, then x times x plus z times z will eventually become larger and larger. But if we keep increasing x and z, the value will wrap around again and again. This is why blocks appear again at some places far away, which is called the second ring. Suppose we have x equals 65536, z equals 0, x times x plus z times z will be 4294,967,296. And since this one minus the same value equals naught, you say what? Why we need to subtract
4294,967,296
naught
2147,483,647.
This is because an entire term of 32 bits is 2 to the power of 32, which is the maximum value of a 32-bit signed integer. So exactly at x equals 65536, it will wrap around to 0. When we take the square root of this value, using the max square root function, it returns 0, which is valid. Thus, after scaled by 8 at the point 524,288, y0, blocks reappear again. The disappearing and reappearing loops continue as we increase the x and z further, and we can derive some formulas to calculate the exact points. Denote distance from the original point as r. For r squared, it's always increasing. But we want to find the points when it wraps around. And do not forget Minecraft generates the end in terms of 8. In other words, we seek for r over 8 squared equals n when mod by 2 to the power of 32, where 0 smaller or equal to n smaller or equal to 2 to the power of 31. On the graph, it obeys a region like this. And so does in Minecraft. To further locate some exact point, let's consider a sinusoidal oscillation. And for the positive part, we have blocks, while for the negative part, we have no blocks. Thus, we should have a period of 2 to the power of 32 times a to the power of 2. Thus, that omega equals 2 pi over 2 to the power of 32 times 64, which equals approximately 2.2858 something to 10 to the power of minus 11, which is really a small number. In this way, the formula is y equals sine 2.2858 times 10 to the power of minus 11 times r squared, where y is the height value and r is the distance from the original point. And for the positive part, we have blocks, while for the negative part, we have no blocks. 感谢大家看到这里。这些视频的录制和制作过程都是我有史以来耗时最长的一集，它的整体代码超过了1700行。这次也首次尝试了关于计算机代码编程相关之类的基础学科，给个一键3连啦，谢谢。